As promised, let's take a look at Problempalooza number 15, circuit logic. In this problem, we're not going to show lots of work here, but I will walk you through the steps. R1, R2, and the battery are in parallel with each other. I know that because they have these convenient little junctions that are on either side of R1, that are on either side of R2, and either side of the battery. So these have the same voltage as each other, requiring the current through R1 to be 6, the current through R2 to be 3, and that makes the total current 9 by junction law. That 9 amps of current is going to split up. 6 of it goes along this path, 3 of it goes along the outside path, but it's still 9 amps total. So it leaves the battery at 9 amps, splits along the 2 paths, and recombines to 9. I don't have to do that for number 2 though. The 2 amps that goes through the battery is trapped. It must go through R1, it must go through R2, it has to go through R3 because these are in series with each other. And it goes through the supply as well. Multiplying across the row, this gives a voltage drop of 8, 12, and 16. And by loop rule, the supply has to give enough energy to the loop so that an electron can make it through these 3 obstacles. So, in order to make it through a loop of V1, V2, and V3, the battery must have put out enough energy to make it through. This gives the supply a total voltage of 36, requiring the equivalent resistance to be 18. Okay. Number 3 is all parallel. Again, this is all parallel because this junction here is on either side of R2. There's no other resistors between R2 and this junction. There's no other resistors between R3 and this junction. And there's no other resistors between the battery and this junction. So whenever we get the voltage, all 4 of these must have the same value for voltage. I get the voltage by multiplying across the row using Ohm's law, so 36 volts is the voltage for everything in this system. This allows us to get the currents, or the resistances going across, and our current. I know that 2 amps goes along the first path, 3 amps goes along the second path, and 1 amp goes along the outside path. That means the total current from the battery has to add up to 2 plus 3 plus 1. The total current from the battery has to equal 6, so the equivalent resistance here is also 6. Okay, those were the warm-ups. Easy peasies. Now for the bottom 2. This is test level. For the test level ones, we notice that R3 and R4 are along the same path as each other. So if R4 has a current of 3 amps, that current, imagine water, must also go through R3. So current through R3 is 3. Similarly, if R1 has 2 amps of current, that 2 amps must also go through R2. And together that must have come from the battery. So 5 amps goes in, splits up along the 2 paths, and then 5 amps returns to the battery. So we've determined all the currents. We multiply out where we can. Now voltages. Along any closed loop, the supply has to give out enough energy for an electron to make it through the obstacles it meets. So if the loop goes along path 1, 2, the conventional current goes to this junction, goes through R1, then R2. Well, the battery supplies 50 volts. It takes 25 of them to get through R2. So V1 must also be 25. And similarly, if I took path 3 or 4 instead, that would still need to give enough energy to make it through the loops. So 50 has to be equal to 10 plus something. That something is 40, and we are good. We solved this problem. With problem 4 on the first page, what we want to do is we want to look at our voltages in parallel. Since R1 and R2 are in parallel with each other, these each have a voltage of 12 volts. Similarly, R3 and R4 have a voltage of 24 volts. And since we're doing all the voltages at the same time, that means the supply voltage is 36. Now, careful with the double counting here. Loop law says that if you take any one path through the circuit, the supply has to equal the voltage used by each of the voltage drops. But that's path independent, so if we went over V1 and V4, that should sum up to the battery voltage. And that's why we wouldn't double count the 12 for both R1 and R2. It would count one time, making the battery voltage 36. Then, solving across with Ohm's law, this leaves the current as 6 and 3, and then again a 6 and 3. Using the junction law then, if you imagine that the 6 and 3 currents at any particular junction are going to recombine. This means 6 amps goes in through R1, 3 amps goes in through R2, making 9 amps total current. The junction rule makes sure that you don't double count this as 18 amps. This is only 9 amps total. Solving across the row then, that gives the equivalent resistance of 36 divided by 9, or 4 ohms. If you're watching this video later in the unit, you can check that this is a 4 ohm equivalent resistance using the equivalent resistance method. Now for the harder problems. To start off, I see that we have a lot of known currents, so it probably indicates we should start with current in this case. In this case, we see that there are 3 amps of current that go through R4. We see that there are 7 amps of current that go through R5. And that means the total current in the series must be 10 amps. That gives us the supply current, and also by multiplying across the row, we can get the equivalent resistance of 4.6 ohms. Following that current around the circuit, the 10 amps will split up between 3 and 7, but recombine again and flow through the battery. That same 10 amps of conventional current hits the next junction and splits up such that 3 amps goes through R1, 4 amps goes through R2, and therefore, in order to satisfy junction rule, there has to be 3 amps go through R3. 3 amps have to go along this path so that the charge that enters the junction is the same charge that goes out of the junction. Multiplying across this row using Ohm's law gives a voltage drop of 18 over all 3 resistors that are in parallel here. These 3 resistors have a voltage drop of 18 each, which allows us to find the resistance using Ohm's law dividing across rows, 6 and 4.5. Finally, we can get the voltage from R4 and R5. These two should be equal to each other because they're in a parallel circuit. And by loop law then, along any closed path, the battery has to supply enough voltage to make it through both sets of resistors. So I arbitrarily picked a path that starts and ends at the battery. An electron would travel through R1, then travel through R4. So 46 has to equal 18 plus the voltage drop over V4. Therefore, V4 must have a value of 26 volts. And since it's in parallel with R5, this also has a value of 26 volts. Dividing across the row then, 28 volts. Dividing across the row then, we can get the equivalent resistance for each set of the circuit. So let's do that again. We've got a circuit that has 4 sets in parallel. Those must all have the same voltage as each other. So this is 4 sets of 10. We can use that to get the remaining currents in those sections. So half an amp goes through R1 and 2.5 amps goes through R3. Looking at current, I see that there are 5 amps of current that flow through R5. Because it's a series circuit, if 5 amps goes through R5, that same current must flow through R6 and the battery before splitting up at the junction. If 5 amps goes into the junction and it splits up over the paths, the sum that goes in has to equal the sum that goes out. So if 5 amps goes in and half an amp goes through R1, 2.5 amps goes through R3, and 1 amp goes through R4, that means R2 must have had a current of 1 amp so that it sums to 5. That gives a resistance of 1. R4 has a resistance of 10 in order to satisfy Ohm's law. Voltage drops of 25 and 30 also emanate from Ohm's law. And so you have a choice here. If you know how to calculate equivalent resistance, you can do that method. But it's probably faster to do the loop law to determine the supply voltage and divide across. So I'm going to pick any closed loop that starts and ends at the battery. So let's say it goes from R2 to R5 to R6. The battery must have supplied enough energy to get through that whole circuit. So that means the total supply voltage is 10 plus 25 plus 30, or 65 volts. Dividing across the row then, 65 divided by 5 means there's an equivalent resistance of 13. I like the problems on the back page better than the front page because it's much more obvious when things are in series versus parallel. In fact, for these two, I'm just going to do all the parallel rules at once and all the series rules at once. The parallel voltage rule means that R1 and R2 have the same voltage as each other, 6 and 6. R4 and R5 have the same voltage as each other, 8 and 8. I put a little box around these so I know not to double count. Similarly, R1, 2, and 3 have voltages of 18. They're in parallel with each other. And, okay, maybe I don't know what this voltage is yet, but I do know that V5 and V6 are equal to each other, so I'm going to put a box there indicating equality. That was all the voltage rules. Let's do all the current rules. I see that in this circuit Sudoku, there's a current of 3 and a current of 2 that go into this junction. 3 amps goes through R1, 2 amps goes through R2, and that means 5 amps must go through R3 using the junction rule. That same 5 amps travels along the circuit and splits up at R4 and R5. If 1 amp goes into R4, then 4 amps have to go into R5. the current recombines through R6, flows through the battery, and restarts. This allows us to find almost all remaining segments of the circuit by Ohm's law and multiplying across this row. I'm going to go back and do the current for the last one on this page. This one says that 12 amps of current leaves the supply. It splits up at this junction, but we actually don't know quite enough information for that. We need to do 18 divided by 3 to get 6 amps here first. So if I know 6 amps goes through path 3, 2 amps goes through path 2, that leaves 4 amps to go through path 1 in order to sum to 12. And divide across as needed. That same 12 amps flows through R4 because it's only one path. It splits up at the junction so that 8 of it goes through R6. So that 4 amps must go through R5 to make your 12 total. If you picture this as gallons of water, that's a helpful analogy. This system has 12 gallons of water that might split up and go through different pipes at any given time, but it still needs to be 12 gallons. Multiplying across all the rows as needed here, this gets a voltage drop of 48 over R4, of 8 over R5, and R6 because parallel. It gives us resistances here, where if you knew how to calculate equivalent resistance in a different method, you could do that to check. Or you can use loop laws in both of these cases to finish the problem. According to loop law, whichever path I take, as long as it starts and ends at the battery, the voltages have to be equal. So in this case, I'm picking path 1, 3, 4, 6. Starts and ends at the battery, hits all the complete circuit. So if the battery puts out 30 volts, R1 uses up 6 of them, R3 uses up 15, and R4 uses up 8, then V6 must be 1 volt in order to have conservation of energy. Someone asked me, can a resistance be less than 1? Yes, it can. So just because this is a fraction or a decimal doesn't mean you did it wrong. It should be a fraction in this case. Same deal on this one. Picking any closed path. Let's pick path 1, 4, 6, 7. That starts and ends at the battery. 18 volts occurs over R1. It takes 48 volts to get through R4. Big expenditure of energy there. 8 and 6. This gets a power supply voltage of 18 plus 48 plus 8 plus 6, or 80 volts. That gives an equivalent resistance in this problem of like 6 and change. 6.6 repeating ohms. Number 10 was the problem I said was not self-consistent. Please erase the 30 before you solve this, or else the problem doesn't work. Okay? So let's deal with current first, since we know the total current of this circuit. In this circuit, we know there's just under 1 amp of current that comes from the battery. So anything along this path has the same current as the battery, the 0.96 amps. That means R1 has a current of 0.96, and I would fill in as a reasoning for B. I would fill in as a reasoning that this has the same current as battery. Using the current rules, I can also see that having 0.61 amps go through R6 means that everything along the outer path here must have current that sums to 0.96. So using the junction rule, 0.6 plus something equals 9.6. That something must be 0.35. The current of 0.35 flows not only through the 30 ohm resistor, which is the one that's right next to the 0.35 symbol here. I would say for that one, for E, the reason that would be junction or node rule. But R2 has the same current as R3 because it's in series. The same current that goes through R2 must go through R3. Now would probably be a good time to use Ohm's law and get a bunch of things out of the way. Using Ohm's law, we get a voltage drop of 72 volts over R1. So under A, I would write Ohm's law. We get a voltage drop of 0.35 times 50, so a 17.5 voltage drop. And this is Ohm's law for C. We get a voltage drop of 0.61 times 20 for J, that's 12.2. And J, I would write Ohm's law for reasoning. And finally, K, 100 divided by 0.96 gives you 104 and change for resistance. Ohm's law. And now we're almost done. I see that R4 and R5 are in parallel with each other. So if I can find one of their voltages, I can find their voltages and currents. So I'm going to use loop law for this. Let's say I pick a path that starts and ends at the battery. The battery has electrons that go through V1, V5, V6, and return. The battery puts out 100 volts. R1 uses up 72 of them. R6 uses up 12.2 of them, and that means V5 must be 100 minus 72 minus 12.2, or 15.8 volts. And not only is V5 15.8, so how about let's put in for H, this is loop law. Loop law goes with voltage, junction law goes with current. Box F is also 15.8 because it's in parallel with R5. And then divide across the row, we know these two are solved by Ohm's law. And we're good. Good luck, guys.